Okay, so optimization is basically an application of curve sketching. So we found out what maximums and minimums are for certain functions and curves. Now we're going to try to put them into real world situations. Okay, so when you get a job and you are having to figure out, or maybe it's your house and your kids are in ag and you have a certain amount of fence and you want the most area for that fence, you can use calculus to figure out the answer. All right, so here we go. There are several types of optimization problems. There's where you want to maximize the volume. Okay, so for example, if you worked at Coca-Cola and you wanted to get by with putting the most volume of Coca-Cola in the smallest package where you needed the least amount of materials. I mean, if you think if you bottle 10 million bottles a day and you can save a penny on materials, you're saving a lot of money. So you would minimize. So you could use calculus to come up with that. Minimize the distance. So that was kind of the example I was given with the fencing. All right, if you have a large piece of property and you want to divide it into a certain number of parcels and you want to minimize the amount of fence that you're using, that you could use calculus to do that. Minimize the area, minimize length. There's others. You could maximize the area, all those kinds of things. So an example. A manufacturer wants to design an open box having a square base and a surface area of 108 square inches. What dimensions will produce the box with the maximum volume? Okay, so you want to minimize the amount of surface area because that's what you're paying for, okay, as far as like materials, and you want to maximize the amount of volume that goes in there. So the strategy. First thing, you have an open box. What does open mean? No top. Which doesn't seem like a big deal, but are you going to have materials on that top? No. So you don't have to count that one. Has a square base. That's important. We want to know that. Has a surface area of 108 square inches. What dimensions will give me the maximum volume? So the strategy, write a function and use derivatives to find the maximum volume. Okay, so we're going to start by writing the primary equation. This is the equation that they're talking about maximizing or minimizing. So they've talked about surface area, they've talked about volume. Which one is the one they want to maximize or minimize? Volume. So volume is our primary equation. So what is the volume of a box? V is equal to the base, which they've told me what is the base? Square, times the height. So volume is equal to x squared, that's the volume of the base, times the height. Questions so far? Find the secondary equation. All right, and the secondary equation is basically one that we're going to use to rewrite the primary equation in a single variable. Right now the primary equation has two variables, x squared and h. I want to eliminate one of those. So I'm going to use the secondary. And this time the secondary is the other information they give me. It's surface area. So surface area is equal to the base, which is x squared, right? Plus the four sides, which is 4x times h. And there's no top. Y'all with me on that? And that equals 108. All right, so this is the base. These are the sides. All right, so trying to eliminate a variable, I'm going to use this, and I get x squared. Can y'all? Am I writing in where y'all can see it? X squared plus 4xh is equal to 108. 4xh is equal to 108 minus x squared. H is equal to 108 minus x squared over 4x. Okay. If I plug this in for H into my volume equation, I've eliminated H from that equation, right? It's now all in terms of X. So V is equal to x squared times H, which is 108 minus x squared over 4x. Cleaning this up a little bit, that x and one of those is going to go away. And volume ends up being x times 108 minus x squared over 4. So volume is equal to 27x minus 1/4 x cubed. Everybody with me on that? All I did was distribute. So that's my equation for volume. Any questions on that? Just eliminating a variable. If you took physics last year, you did a lot of this. We eliminated variables all the time when we were solving force problems. Tension and acceleration and all that stuff. Okay. Now, determine feasible domain. That's real life problems. Okay, like in real life, x has to be greater than 0. Okay, has to be, the volume has to be something. Okay, if you have a surface area of 108, I suppose you could just have a flat bottom with no h in it, but it doesn't make sense for a box to be like that. So any negatives are not going to work for us in this case. Okay, so if the height is 0, then a is equal to x squared, which is equal to 108. Okay, is everybody with me on that so far? So in this case, my very smallest number that I can get here is whenever I set x squared is equal to 108, which means that x is equal to plus or minus the square root of 108. But what did we say about minuses? They're not feasible, so positive square root of 108, which is equal to 6 square roots of 3. Okay, so my smallest x is 0, which doesn't really make a lot of sense, but that's the smallest. And my biggest is going to be this. This is my domain. Those are my endpoints, I guess is what I should say. And why do endpoints matter in curve sketching? Endpoints can be what? Maxes. That's right. They can be max or min. So the endpoints matter. So this is what I want to know here. Okay, now find the critical numbers. How do I find critical numbers? How did I do them before in curve sketching? Do I remember how I found the critical numbers? Starts with a D, ends in derivative. Derivative, good. All right. So V prime is equal to the derivative of 27x minus 1/4 x cubed, which turns into 27 minus 3/4 x squared. Okay, I'm going to just write this so that we remember. All right. And I need to set that equal to 0. So that means 27 is equal to 3/4 x squared. What's 27 divided by 3? 9 times 4. 36 is equal to x squared.
Square root of that is 6.
So 6 is equal to x. So So then, what I need now, so I'm basically walking you through the steps. Do y'all see that? Next step is to evaluate all critical numbers and endpoints in the domain that I had to find. So V sub 0, because that's an endpoint, that's 27 times 0 minus 0. What is 0 minus 0?
0.
Okay, that's how much volume I get whenever x is equal to 0. V6. 27 times 6 is something pretty big. So this is 27 times 6 minus 1/4 times 6 cubed. All right, so when I plug that in, I get, is that better?
It's like you zoomed in.
Wow. Yeah, I don't know. Okay. 6 cubed is 216 divided by 4. 27 times 6 minus 54. I get 108. So that equals 108. All right, and then finally the volume when 6 square roots of 3. And that actually turns into 0 also. So which is my maximum volume?
6.
When x is 6. All right, so max volume occurs.
No, it's like
zoomed in on the upper right corner.
Did you see it glitch out just there?
No. Did it change?
Yeah, it zoomed in and zoomed out.
Zoomed in, zoomed in again, and then zoomed back out.
Occurs. At x equals 6. Okay. So 6 by 6 by 3.
That's the bit is the maximum volume.
That's the max volume. Okay, so x is 6. I can go back to my to this surface area to find height. So h is equal to 108 minus 36 over 4 times 6, which is 24, and I get my volume. So max volume occurs there, and that's when it's 6 by 6 by 3 box. Okay. Got it? Okay, next one. It says 2 posts, one 12 feet high and the other 28 feet high, stand 30 feet apart. They are to be secured by 2 wires attached to a single stake, running from ground level to the top of each post. Where should the stake be placed to use the least amount of wire? Okay, so kind of confusing. First thing, draw a realistic diagram. So do that at your desk in pencil. Select variables. I just picked X, Y, and Z because those were the first ones that came to mind. Okay, so the distance is 30. I labeled this little triangle X, there's Y, there's Z, and there's 30 minus X. You could have labeled them whatever you wanted. but X, Y, and Z, get the little A, B, and C. All right, and it says, everybody got that? Does that make sense to everybody?
Now it does.
Okay. It says that we're trying to what? What is it that we're trying to do? What are we trying to maximize or minimize?
Minimize the wire.
Minimize the wire. So what's our primary equation?
Minimize the wire.
Yeah, it's the wire equation. And so from my diagram, what is the amount of wire equal to?
30.
That y plus z. All right. All right, next thing. I need another equation, the secondary equation, that hopefully will relate stuff together. Okay? That's what I want to do. So, what other equations are here? I mean, there's not a lot. Pythagorean theorem equations. So, I've got x squared plus 12 squared, which is 144, is equal to y squared. So, y is equal to the square root of x squared plus 144. And then I have this other one, which is 30 minus x squared plus 28 squared, which is 784, which is equal to z squared. So z is equal to 30 minus x squared plus 784. Square root of all of that. Okay, so I've got y in terms of which variable?
X.
And I've got z in terms of which variable? And my primary equation is y plus z. So if I replace y with this and z with this, which variable am I dealing with?
X.
X. So we're in good shape. That's what we wanted to do. All right. I'm going to move over to here. Okay. So, so what is a reasonable domain for, well, let's rewrite this. The wire.
Mr. Barry, we have like 1 minute left.
Are you serious? Okay, we're going to stop here for today then.